good. So just some basic information about the project. Storm was open sourced September 19th of last year. The implementation is only 15,000 lines of code. About half of that is Java and half of that is Clojure. Even though Storm hasn't really been around that long, it's already been adopted by over 25 companies. And it has a pretty active community. There's a lot of watchers on GitHub, and has a very, very active mailing list. So before we get into the guts of Storm, I want to talk first about how we used to build these systems before we had Storm. And kind of the purpose of this is to see what are the intricacies of real-time computation that made us go and build a whole new system. So the paradigm we used before Storm was to build our real-time systems using the queues and workers paradigm. So it's a very, very common paradigm. We certainly were not the first ones to try this. So our system looked like this before Storm. So we had an application that was processing the Twitter fire hose. And what we would do is we would put the tweets onto a set of queues, and then we had a set of workers reading those tweets, and the first set of workers would put those tweets into our schema, append those tweets into Hadoop for later processing, and then pass some data in those tweets off to a second set of workers for further processing. That second set of workers would look at any URLs that are being tweeted and then update statistics on those URLs by incrementing various counters in Cassandra. So we do things like look at number of tweets per URL over time, or impressions per URL over time, and things like that. Now, one of the interesting things about this portion of the computation is that we had the requirement that the same URL is always processed by the same worker. So we couldn't ever have two URLs being, or the same URL being processed by multiple workers. And the reason for that is because Cassandra doesn't have transactions, and at the time it didn't have atomic counters. So if we didn't have this property, then you'd have a race condition, and then workers would trample on each other, and you would lose increments in Cassandra. So the way we made sure the same URL always went to the same worker is we would actually hash the URL and mod the hash by the number of consuming workers to choose the worker to send the URL to. And this technique makes sure the same URL always goes to the same worker, but it still distributes the URLs so that you can distribute your processing. So this system worked for us for a while, but it had a lot of problems. And one of the problems was actually you would see when you would try to scale a system like this. So for example, let's say that we needed more workers for the portion of the computation that was updating the statistics in Cassandra. Well, to do this, you'd have to, well, first of all, deploy a new worker for that set of workers. And then you'd actually have to go and reconfigure and redeploy the first set of workers that are sending messages to those workers. The reason is that because it's doing that hash mod technique, it now needs to know there are more workers. So you see these kind of like cascading changes throughout your system when you change one portion of it, and then you need to update other portions of it because there's kind of dependencies all over the place. So there were a lot of problems with this system. So like I said, scaling it was painful. Another big problem was that the fault tolerance of the system was very, very poor. You kind of just had to make sure your queues and workers stayed up. There's things you can do by having failover among workers, but it all ends up being very tedious and it ends up being pretty brittle. And then finally, one of the worst problems is that coding these things is very tedious. Almost all your code has to do with where do you read messages from, where do you send messages to, how do you serialize messages. The actual real-time logic you care about ends up being a small percentage of your code base. Okay, so when we looked at this problem and various other real-time problems we had, we came up with this list of properties that we want from a good real-time computation system. So the first property is that a real-time computation system must guarantee data processing. Too many applications require this. The second is that it must be horizontally scalable, but not just horizontally scalable, but easily horizontally scalable. So add nodes, tweak a few knobs, and have everything just work. The third property is it must be fault tolerant. So if there's any errors at runtime, it should self-heal, launch workers somewhere else, do what's necessary to keep the computation running. The fourth property is an interesting one. So I say here, we wanted to get rid of all those intermediate message brokers. Right? So if you look back at this diagram, between every set of workers, you have this set of queues. Now the problem with these intermediate message brokers is that they're actually fairly complex. It's a major moving part, pervasive through the whole architecture, and it's also slow. So instead of being able to send messages directly from one set of workers to another, you're going through a third party, and even worse, that third party has to persist that message to disk. But the reason we have those intermediate message brokers to begin with was for that data processing guarantee. The idea is if a worker fails to process a message, it can just get the message again from the queue because it was persisting it. So if we get rid of those intermediate message brokers, we need a whole new strategy for guaranteeing data processing. So the fifth property we wanted was a higher level abstraction than message passing. Message passing is clearly too low level for this kind of computation. And finally, the last property is that a real-time computation system needs to be extremely robust. So a point of comparison that I like to make is with Hadoop. So how many people here have used Hadoop before? Okay, a lot of people. So I'm sure all of you have experienced the pain of Hadoop. It's very common to get some crazy stack trace. I've been using Hadoop for like more than 3 years, and I still get these crazy problems where you have to dig into the implementation of Hadoop and discover some crazy configuration that you need to tweak just to get the thing running again. So it's very common to take a few hours of downtime in your processing on Hadoop, or sometimes even worse. But in some ways that's okay for Hadoop because Hadoop is fundamentally a high latency system. So if you take a few hours of downtime, you're still high latency, just a little higher latency. With a real-time system, if you take a few hours of downtime, you're no longer real time. So the robustness requirements are much, much higher. And obviously Storm satisfies all these properties. I wouldn't have mentioned them if it didn't. So there's 3 broad sets of use cases for Storm. These are by no means all-inclusive, but it's a good way to think about the kind of things you can apply it to. So the first use case I call stream processing. So the idea here is you're processing a stream of, let's say, tweets, and then you're updating databases, let's say, statistics in those tweets. The second use case I call distributed RPC. So the idea here is that you can implement, or the idea here is that you have some function that you want to compute on the fly, but it's a really intense function to compute. So what you can do is you can actually implement that as a Storm topology, and then use Storm as an RPC mechanism for parallelizing the computation of that function. It's a really powerful technique, and I'll talk more about this later on in this talk. The third use case I call continuous computation. So the idea here is that you have some function which you continuously want the results to. So an example of this is computing, let's say, trending topics off of the Twitter fire hose. Okay, so a Storm cluster looks like this. There's 3 classes of nodes in a Storm cluster. The first is called Nimbus. This is the master node. Plays a role similar to the Hadoop job tracker. Nimbus is where you submit your topologies for execution. So you give it like your jar containing your code and then your topology. Nimbus will go ahead and distribute your code around the cluster, and then it will launch workers to run your computation. Nimbus will also monitor your topology and then restart workers somewhere else if any problems happen during runtime. In the middle is the Zookeeper cluster. So Zookeeper is an Apache project. Zookeeper is basically a cluster coordination system. That's exactly what the Storm uses it for. Then on the right, you have a set of worker nodes. This is where all your processing actually happens. Each worker node has a daemon on it called a supervisor. And the supervisor communicates with Nimbus through Zookeeper to determine what should be running on this machine. And then the supervisor will start and stop workers as necessary, as dictated by Nimbus. Okay, so let's say you have something you want to run on a Storm cluster. Here's how you would launch it. So Storm has a command line client called Storm, very similar to like Hadoop's command line client. So to launch a computation, you would say Storm jar, give it a jar containing your code and dependencies, tell it the class to run, and then the arguments to that class. Now Storm computations, which are called topologies, they actually run forever. But if you ever want to stop a topology, you can kill it using a command like this. We say Storm kill, and then the name of the topology. All right, so let's dig into the concepts of Storm. So there are 4 main concepts in Storm: streams, spouts, bolts, and topologies. So stream is the core data model in Storm. Storm is all about manipulating streams and transforming streams. And a stream is just an unbounded sequence of tuples. And a tuple is just a named list of fields. And then the actual values in your tuples can actually be of any type. If you use a type Storm doesn't know about, you can provide a serializer for it. Next, you have spouts. So spouts are a source of streams in a computation. So examples of spouts are, let's say, a spout that reads off of a Kestrel queue or RabbitMQ queue, or maybe you have a spout that connects directly to the Twitter streaming API and emits that as a stream of tweets. Next, you have bolts. So bolts process any number of input streams and produce any number of new output streams. So most of your logic goes into these bolts. So you can do anything from run functions, do filtering, do streaming aggregation, streaming joins, talk to databases. Like I said, most of your logic goes into these bolts. Okay, so finally, the top level abstraction in Storm is called a topology. And a topology is just a network of spouts and bolts, where every edge in the network just indicates a bolt subscribing to the output stream of some other component. So the key to Storm is that spouts and bolts are inherently parallel. They execute as many tasks across the cluster. And then those tasks actually communicate directly to one another. So if you look at this diagram, the spout on the left has 2 tasks, the bolt on the top has 3 tasks, and the other 2 bolts each have 2 tasks. If you look at how it looks, so this is the kind of logical level. If you look at the physical level, right, you have your worker nodes, and then Nimbus and the supervisors will spawn some number of workers for your topology, and each worker contains some number of tasks. So let's say your spout, which has 2 tasks, one task may be running in the worker on the bottom left node, and the other spout task may be running on a different worker on some other node. You can see just the spouts are just spread all around the cluster, right? And those tasks communicate directly to one another. So this brings up the question of when a task emits a tuple, which task does it send the tuple to in the consuming bolt? Right, so here we have a bolt with 3 tasks on the left, sending messages to a bolt with 2 tasks on the right. When a task on the left emits a tuple, which of the 2 tasks on the right does it send a tuple to? So you answer the question in Storm by providing what's called a stream grouping. So the simplest kind of grouping is called a shuffle grouping. So in this case, it actually just picks a random task to send a tuple to. And this has the effect of evenly distributing the load of processing that stream. A more interesting kind of grouping is called a fields grouping. So in this case, it chooses the target task by doing mod hashing on a subset of the tuple fields. So this should sound awfully familiar to what I was talking about in the beginning of my presentation, except it's done at a much higher level of abstraction. Another kind of grouping is called an all grouping. So in this case, it actually replicates the tuple to all tasks. Obviously, this blows up the size of your stream, so this is something you generally use with care. A global grouping sends the tuple to the task with the lowest ID. This has the effect of having just one task process everything. And there's some other kinds of groupings, but those are beyond the scope of this talk. So if you actually look at a topology, it looks something like this, where you actually annotate every stream subscription edge with the kind of stream grouping used. All right, so I've done a lot of talking, so let's get into some code. So what I'm going to show is an example of implementing streaming word count on top of Storm. So the idea behind streaming word count is that you process an input stream of sentences, and then you emit an input stream of word counts, where you kind of just emit a new word count every time you see the word again. And the count is just the total number of times you've seen that word before. So the first thing you do is, so if you're creating a topology in Java, first thing you do is you create this topology builder object, which provides a nice API for constructing these topologies. So let's create our first spout. So we'll create a spout. You say builder set spout, then you give the spout an ID. So here we name it spout, and then you give it the implementation of the spout. So here we say we're going to use the Kestrel spout, and we're going to read off of that host and port, or off of that host and port and queue off of that Kestrel server. And then at the bottom, we give the spout a parallelism of 5. So there'll be 5 tasks launched across the cluster. Each of those tasks will hit that Kestrel server asking for new messages.